What if solving an equation forced you to believe in a particle that no one in the history of humanity had ever seen before? A particle that seemed to break the rules. One that mirrored ordinary matter, yet had never been observed. In 1928, Paul Dirac wasn't searching for this particle. He was just trying to make quantum mechanics compatible with Einstein's special theory of relativity. He was searching for a new type of relativistic wave equation. But what he found was far more profound than anyone could have anticipated, because his equation didn't just describe known reality, it revealed something entirely new: antimatter. In part 1 of this series, we explored the road that led to Dirac's equation. We saw how the Klein-Gordon equation broke the rules of quantum probability, and how Dirac's demand for elegance led him to a bold new formulation, one that required an entirely new kind of wave function: the 4-component spinor. But what exactly is a spinor? What do its components represent? And what happens when we actually try to solve the Dirac equation? To address these questions, we require a strategy. In this video, we will begin by solving the Dirac equation for a stationary particle and uncover its energy spectrum. We will then see how negative energy states emerge and why we can't just throw them away, before extending the solution to moving particles. We will then reinterpret the negative energy solutions as antiparticles and show how Dirac predicted the positron. And finally, we will reveal how the structure of the equation itself encodes an intrinsic angular momentum, what we now call spin. This is the story of how one equation reshaped our understanding of reality, again. So buckle up and enjoy the ride. To start with, let's remind ourselves of the structure of the Dirac equation when written in component form. The equation is first order in time derivatives and involves a vector of 4x4 matrices known as the alpha matrices, as well as the 4x4 beta matrix. We note that the right hand side also contains the gradient vector and its first order in space derivatives, and the dot product takes the following form. We will be working with a particular representation of the 4x4 alpha and beta matrices expressed in terms of the Pauli matrices. And since the alpha and beta matrices are 4x4, it follows that the wave function which they act upon must be a 4-component object known as a Dirac spinor. Our task is to now try and solve this equation. We begin with the simplest possible case, a free particle. One not experiencing any forces, moving through space with a constant momentum p. In this case, we can try a plane wave solution of the following form, where u is a 4-component spinor that doesn't depend on time or space. Rather, all the dynamics are carried in the exponential factor. Okay, so let's take this proposed plane wave solution, and let's begin by subbing it into the left-hand side of the Dirac equation. If we do this, we find the following result, where we've pulled out a factor of e from the exponential, and we also note that we've written the spinor as u to simplify the notation and keep our expression as streamlined as possible. Next, we sub the plane wave function into the right-hand side, and we find the following expression. To evaluate the first term, we note that acting on the exponential term with the gradient operator pulls out a factor of momentum. If we then apply this to the right-hand side expression and recall that the spinor u does not depend on space, and therefore acts as a constant, we find the following compact expression. Next, we can cancel the exponential factor from both sides, and then we are left with the following equation. This is known as the time-independent Dirac equation in momentum space. Next, we're going to consider the case of a stationary particle, corresponding to a momentum vector 0, 0, 0. In this case, our eigenvalue equation simplifies, and we end up with the following equation, which we'll now solve to find the allowed spinor solutions. To make things neater, let's divide both sides by mc squared, and then define lambda equals e over mc squared. We then see that our equation takes the form of an eigenvalue eigenvector equation, where the spinor u is playing the role of the eigenvector, and lambda is the corresponding eigenvalue. To make this more explicit, let's rewrite our equation in block matrix form by writing our spinor U in the following form, where UA and UB each have two components, and where beta takes its standard matrix form. In this case, our equation becomes the following expression. If we then evaluate the left-hand side by performing the matrix multiplication, we find the following green expression. And then we use the fact that the identity matrix acting on UA gives back UA, and likewise for UB. And so we can write our equation in the following form. And we see that we now have a set of two equations. UA equals lambda UA, and UB equals minus lambda UB. Let's now consider the first equation, UA equals lambda UA. We immediately see that if UA is non-zero, then the only consistent solution is lambda equals plus 1. And in this case, UA can be any column with two complex components. For example, we can write UA as the column phi1, phi2. Next, if we consider the second equation, then if UB is non-zero, then the only consistent solution is lambda equals minus 1. And so we see that in this case, UB can also be any column with two complex valued components, such as UB equals phi3, phi4. And so we see that our eigenvalue equation with lambda equals E over mc squared has two possible eigenvalues corresponding to lambda equals plus or minus 1. In the case that lambda equals plus 1, we see that this gives E equals mc squared, which corresponds to a positive energy solution of the Dirac equation. On the other hand, in the case that lambda equals minus 1, this gives E equals minus mc squared, corresponding to a negative energy solution. Okay, so let's now zoom in on the lambda equals plus 1 eigenvalue corresponding to the positive energy branch. If we write out our equation in block form and multiply through and simplify, we see that we end up with two conditions, UA equals UA and minus UB equals UB. We see that the second condition immediately implies that UB equals 0, whereas for UA not equal to 0, we can write UA as a column of two complex components. And so it follows that a general positive energy solution, which we will denote U+, takes the following form. In other words, for positive energy, the lower two components vanish and the upper two can be any arbitrary complex numbers. We can also express this solution as a linear combination of two independent basis spinors E1 and E2, where E1 equals 1, 0, 0, 0 and E2 equals 0, 1, 0, 0. Okay, so now let's go back to our eigenvalue equation, but this time consider the case where lambda equals minus 1, which corresponds to the negative energy branch. As before, we write the equation in block form, multiply out and simplify, and we find two conditions, UA equals minus UA and minus UB equals minus UB. And we immediately see that the first condition implies that UA equals 0, whereas the second implies that UB can be any two-component column of complex numbers. And so we see that a general negative energy solution, which we write as U minus, can be written in the following form. Again, you can write this as a linear combination of two independent basis spinors E3 and E4, where E3 equals 0, 0, 1, 0 and E4 equals 0, 0, 0, 1. And so, to summarise, in the case of zero momentum, we found that any positive energy solution can be written as phi1 E1 plus phi2 E2, and any negative energy solution can be written as phi3 E3 plus phi4 E4. Okay, so let's pause a moment and take stock. We began by proposing a plane wave solution of the following form, and then we considered a particle with zero momentum. In this case, we found that the Dirac equation admits both positive and negative energy solutions. In the positive energy case, where E equals plus mc squared, we can write our wave function as U plus times e to the minus I mc squared t over h bar, And since U plus can be written as a linear combination of basis spinors E1 and E2, we can express the full solution as psi1 plus psi2. These are two independent solutions of the Dirac equation corresponding to positive energy at rest. Together, they span the full space of positive energy spinor solutions in the zero momentum rest frame. On the other hand, in the negative energy case, where E equals minus mc squared, we can write our wave function as U minus times e to the plus imc squared t over h bar. And since U minus can be written as a linear combination of the basis spinors E3 and E4, we can express the full solution as psi3 plus psi4. These represent two independent negative energy solutions of the Dirac equation in the rest frame. Taken together with the two positive energy solutions we found earlier, we now have four independent spinor solutions in total, and that's exactly how it has to be. And this is because if we tried to throw away the negative ones, if we insisted that all energies must be positive, we'd be left with only half the story, just two solutions, and that's not enough. The Dirac equation demands four. Why? Because it's a first order equation that comes from taking the square root of the relativistic energy momentum relation and writing this in linear form. And as we saw in part 1, this requires the introduction of 4x4 matrices acting on a 4-component spinor. And we've also seen that at rest, the Dirac equation reduces to a simple eigenvector eigenvalue equation. And we know from the diagonal structure of the beta matrix that beta has 4 eigenvalues, 2 plus 1 and 2 minus 1. And this means that the wave function spinor must include 2 components with positive energy and 2 with negative energy. So the negative energy solutions aren't just a weird optional extra, they're essential. Without them, the Dirac equation simply doesn't work. You'd lose half the degrees of freedom, and the equation would no longer describe all possible physical states. The mathematics insists the negative energy states must be there. But what do these negative energy solutions mean? Are they just some weird mathematical glitch, or a fatal flaw like we saw in the Klein-Gordon equation, where, if you recall, we saw that negative energies led to negative probability densities, which completely broke the rules of quantum mechanics? So, does the same thing happen here? To answer that question, we recall that in the Dirac theory, the probability density is defined by the following expression, where the dagger refers to the Hermitian conjugate, which means taking the complex conjugate and then transposing. Now, let's write the rest frame wave function, corresponding to p equals 0, in its most general form as a linear superposition of the 4 basis spinors, where E1 and E2 are equal to plus mc squared, and E3 and E4 are equal to minus mc squared. It then follows that the Hermitian conjugate of the wave function can be written in the following form, and if we then sub these two expressions into the probability density equation and combine the exponential terms, we find the following purple expression. Now, here is the key point. The term EI dagger EJ is only non-zero when I equals j, and in that case it's equal to 1. And this means that all of the cross terms, EI minus EJ in the exponential, will be equal to 0 since EI minus EI equals 0. And in this case, the exponential terms will be of the form e to the 0 equals 1. And so, if we apply this to our probability density, we see that the expression simplifies drastically, and we're left with the sum of the modulus squared of phi 1, 2, 3 and 4. And since the modulus squared of any complex number is always greater than or equal to 0, it follows that the probability density is also greater than or equal to 0. This tells us 3 important things. Firstly, the probability density is always non-negative, no matter what energies the components carry. Secondly, the probability density is constant in time. The time dependence cancels out completely. And thirdly, the negative energy components contribute positively, just like the positive ones. So in short, the inclusion of negative energy solutions does not lead to negative probabilities. That major flaw in the Klein-Gordon equation simply doesn't happen here. The Dirac equation avoids it entirely. So now that we've explored the stationary solutions of the Dirac equation, both positive and negative energy, the natural next step is to ask, what happens when the particle isn't at rest? We'll now turn to constant momentum solutions and try to wrap our head around what they look like and what they mean. But before we boost this particle into motion, let's take a quick moment to talk about something else that travels fast: your data. Browsing without a VPN is a bit like leaving your physics homework in the middle of a train station. Everything is visible and anyone can copy it. Now, realistically, no one's going to steal your physics homework, but your browsing history, well, that's a different story. Now, a VPN or virtual private network encrypts your internet connection and hides your IP address. It keeps your data private, even on public Wi-Fi. I use private internet access, or PIA, whenever I'm working away from home. Whether I'm accessing research papers, editing scripts while travelling, or just browsing online, it's been reliable, easy to use, and works across all my devices. It's also really handy when content is geo-restricted. If I want to watch a series or a documentary and it isn't available in the UK, I just switch my server location and refresh. One of the newer features I really like is that a single subscription now covers unlimited devices, so whether I'm on my laptop, phone or tablet, everything's protected. And honestly, this kind of peace of mind is worth it. Whether I'm working from a coffee shop, travelling abroad, or just want to hop onto public Wi-Fi, I know my connection is secure and my data stays private. It's one less thing to worry about. So if you want to try it, just scan the QR code or follow the link on the screen. That will get you 83% off plus 4 extra months free. And there's a 30-day money-back guarantee. So you can see if it works for you with 0 risk. Alright, so let's get back to the physics. Okay, so our task is to now determine whether our plane wave is still a valid solution to the Dirac equation when the momentum is non-zero. If you recall, we showed earlier that when we substitute this plane wave into the Dirac equation, we end up with the time-independent Dirac equation. And we can then write this as a sum over the spatial indices where I equals 1, 2, 3 corresponds to x, y, z. And then our task is to figure out what the spinor u looks like in the case where p is non-zero. To proceed, we will sub in the explicit matrix representation of alpha and beta. Substituting these into our equation gives the following block matrix form, and if we then add together the matrices and rewrite sigma and p as a dot product, we find the following compact expression. If we then write our spinor in terms of two component spinors UA and UB, and then sub this explicitly into our equation and multiply through, we find the following blue expression. And this now corresponds to 2 coupled equations involving UA and UB. Then, using the fact that the identity acting on UA gives back UA and acting on UB gives back UB, we can neaten up our 2 coupled equations, and then if we rearrange the first expression and then make UA the subject, we obtain a compact equation for UA in terms of UB. In a similar fashion, we can rearrange the second equation and make UB the subject. And if we then sub this into the first equation, we find the following purple expression. And this then implies the following matrix equation involving the square of sigma dot p. If we then write sigma dot p squared in component form, and then sub in the sigma matrices, simplify, and perform the matrix multiplication, we find an elegant result equal to the square of the momentum vector multiplied by the 2x2 identity matrix. And then, if we sub in this result, we find that the equation is only satisfied if E squared equals P squared C squared plus M squared C to the 4. And this is exactly the Einstein energy-momentum relation. So this is very reassuring. It means our proposed plane wave solution is indeed a valid solution to the Dirac equation, as long as the energy and momentum are related in the way required by special relativity. The next step is to work out what the spinor u of EP actually looks like when the momentum is non-zero. To do that, let's return to the two coupled equations we found earlier that relate the two parts of the spinor, UA and UB. If we then take our general plane wave solution and write the spinor explicitly in terms of UA and UB, and then sub in the expression for UB, we find the following expression. And then, to find explicit solutions, we will consider the two simplest possible choices for the upper spinor components UA, corresponding to UA equals 1, 0 and UA equals 0, 1. These two choices give us a clean starting point for constructing the full 4-component spinors. To build the full spinor, for each case, we need to compute the corresponding lower component, UB. If we consider the first case with UA equals 1, 0, and sub this into our expression for UB, whilst at the same time writing sigma.p in component form, we find the following expression. If we then perform the matrix multiplication and simplify, we find the following result for UB. If we then combine the expressions for UA and UB in case 1 and label this solution U1, we find the following overall solution, where we have introduced a normalization constant n1. We can then repeat the same process for case 2, and if we sub in UA and perform the matrix multiplication and simplify, we arrive at the following result for UB. And so we can define the solution U2 corresponding to case 2, and we find the following result, where we have introduced a normalization constant n2. It should be noted that the choice of the two orthogonal forms for UA is arbitrary. Any other choice would have been valid, since a general spinor can be expressed as a linear combination of U1 and U2. Okay, so let's pause and take stock. We've now constructed two solutions, U1 and U2, by choosing simple upper components and calculating the corresponding lower components using the Dirac equation. These describe the positive energy solutions in the case where the momentum is non-zero. On the other hand, the two negative energy solutions, U3 and U4, can be found in exactly the same way, except this time we reverse the logic. We start by choosing simple values for the lower component UB, and then compute the corresponding upper component UA. Specifically, if we take UB equals 1, 0 and UB equals 0, 1, and then work through the same steps as before, we find the negative energy solutions U3 and U4. And so now that we've constructed all 4 spinor solutions, 2 with positive energy and 2 with negative, it's always good practice to double check that they really do satisfy the Dirac equation. If you recall, we built these spinors by solving the time-independent Dirac equation in momentum space. So in principle, this relation should hold automatically. It's true by construction. But it's still good practice to check one of them explicitly just to be sure the algebra holds together. For example, let's take U1 and substitute it into the equation to confirm both sides match. If we sub in the explicit form for U1, noting that we're going to drop the normalization constant for simplicity, and combine the alpha and beta matrices as before, we find the following expression. And then if we perform the matrix multiplication, we end up with the following monstrosity. Now we will begin by tackling the upper block. So we take the upper block and then multiply through and simplify, and we find the following purple expression. Next, we note that p squared c squared equals e squared minus m squared c to the 4, and that this can be written as brackets e plus mc squared times brackets e minus mc squared. If we then sub this into our expression, we end up with the simple and elegant result e times 1, 0. Next, if we evaluate the bottom block, perform the matrix multiplication and simplify, we find the following compact expression. And if we then combine the results from both blocks, we see that the final expression is simply equal to the energy multiplied by U1. Now, the term on the left-hand side is what we call the Dirac Hamiltonian. And so we see that we've just established that U1 is one of the energy eigenstates of the Hamiltonian with eigenvalue E, where E equals plus the square root of p squared c squared plus m squared c to the 4. And if we then repeated the same process for U2, U3 and U4, then we would find that each of these are also energy eigenstates, with the energy being positive for U1 and U2 and negative for U3 and U4. And so, in summary, we see that plane wave solutions to the free particle Dirac equation have the following form, with I equals 1, 2, 3, 4, and each of these satisfies the Dirac equation, provided the energy and momentum are related by the Einstein energy-momentum relation. Let's now confirm this interpretation by returning to the zero momentum case p equals 0, 0, 0. In this limit, the momentum-dependent terms in each spinor vanish, and the solutions reduce to simple combinations of the basis eigenspinors we identified earlier. For example, if we take U1 and set p equals to 0, we see that it reduces to a multiple of the basis eigenspinor E1. Similarly, U2 reduces to E2, and so on for U3 and U4. These match exactly the rest frame spinors we derived earlier when we set p equal to 0 in the Dirac equation and found that, with beta acting diagonally, the eigenvalues are E equals plus or minus mc squared. So we can now confidently say U1 and U2 reduce to the positive energy rest frame solutions, and more generally correspond to E equals plus the square root of p squared c squared plus m squared c to the 4, and U3 and U4 reduce to the negative energy rest frame solutions, and more generally correspond to E equals minus the square root of p squared c squared plus m squared c to the 4. The takeaway is clear. The Dirac equation demands 4 solutions, 2 with positive energy, 2 with negative. This isn't optional. It's baked into the structure of the equation itself. The mathematics insists on it. But now that we've established the mathematical necessity of these 4 solutions, especially the 2 with negative energy, we face a deeper question. What do they mean? At first glance, negative energy solutions seem unphysical. Negative energy isn't something we observe in the real world, so are these just mathematical leftovers, best ignored, or do they point to something deeper? But before uncovering the magic, just a quick reminder to hit the like and subscribe button if you want to see more physics deep dives. It really helps the channel grow and reach more people. But now let's get back to those negative energy solutions. To properly understand the concern, consider what the Dirac equation actually predicts. For a freely moving particle with momentum p, the Dirac equation predicts 2 possible energies, one positive and one negative, given by E equals plus or minus the square root of p squared c squared plus m squared c to the 4. Since the momentum can take any value from 0 upwards, the positive energies form a continuous band starting at plus mc squared, and they move all the way up to infinity, while the negative energies form a second band stretching downwards from minus mc squared to minus infinity. And here's the issue. If these negative energy solutions are physically real, then nothing in the equation prevents a positive energy electron from spontaneously radiating energy away and dropping into one of those lower negative energy states. And once it starts falling, it would never stop. There's no lowest rung to land on. The electron would spiral down endlessly, releasing radiation as it goes. This leads to a catastrophic conclusion. The vacuum itself wouldn't be stable. There would be no true ground state. The entire theory would collapse under the weight of its own predictions. And this was the very puzzle that confronted Paul Dirac. His approach to theoretical physics was famously intuitive. He once remarked, A great deal of my work is just playing with equations and seeing what they give. And when he played with his new relativistic wave equation for the electron, the equations gave something strange. 4 solutions, 2 with positive energy, 2 with negative. At first, Dirac tried to dismiss the negative energy states, claiming that half the solutions must be rejected. But as he explored further, he realised he couldn't just throw them away. In June 1928, during a talk in Leipzig, Dirac acknowledged the inescapable reality that transitions to negative energy states could not be ignored. He admitted, "The present theory is an approximation," signalling his growing belief that these puzzling solutions required a proper physical explanation. After discussing the issue with Werner Heisenberg, Dirac's concerns deepened. Heisenberg, equally unsettled, confided in Wolfgang Pauli, writing, "The saddest chapter of modern physics is and remains to be the Dirac theory." The challenge of interpreting the negative energy states persisted. In May 1929, mathematician Hermann Weyl suggested that the 2 pairs of components in the Dirac equation might correspond to the electron and proton. But by December of the same year, Dirac had rejected this idea, pointing out that if an electron transitioned from a positive to a negative energy state, it would violate charge conservation. A proton has positive charge, while an electron is negative. Instead, in 1930, Dirac proposed a far more radical idea. Let us assume that all the states of negative energy are occupied. This idea, known as the Dirac sea, made use of the recently formulated Pauli exclusion principle, which states that no 2 electrons can occupy the same quantum state. By filling all the negative energy states, Dirac argued, we could block transitions from positive to negative energy, because there would simply be no room left. To visualize this, imagine the energy states as rungs of a ladder, with all the negative energy states below minus mc squared, and all the positive energy states above plus mc squared. Then fill all of the negative energy levels with electrons. Now, earlier, we said that the energy spectrum forms a continuous band, and that's true. But to make things easier to picture, we imagine placing the system in a very large but finite box. In this case, the allowed momentum values, and therefore energy levels, become discrete. This is a standard trick in physics. Discretize the system first, take the continuum limit later. So this diagram, with its ladder of filled levels, represents the vacuum. In Dirac's original model, the vacuum is defined as the lowest energy state of the universe. All negative energy states filled, all positive energy states empty. It's the baseline. Crucially, we treat the vacuum as unobservable. It defines the 0 point for measuring energy, charge, and momentum. And here's the key point. With the Dirac sea completely full, the Pauli exclusion principle prevents any normal positive energy electron from falling into the negative energy sea. There's simply no space available. The theory's instability disappears. The vacuum becomes stable. Dirac's trick has worked. But Dirac went even further. He asked, what would happen if one of those negative energy electrons were somehow removed? That hole represents the absence of a negatively charged negative energy electron. And remarkably, it behaves like a positively charged positive energy particle. Let's see why. Let's go back to our earlier idea of placing the universe in a large but finite box. Inside the box, we imagine all negative energy states are filled with electrons. That's our vacuum. The total charge of the vacuum, coming from all these electrons, is a huge negative number. Let's call it Q vacuum. Next, suppose we remove one of the negative energy electrons from the Dirac sea. In that case, after the charge is removed, the charge of the Dirac sea will be equal to the charge of the vacuum minus the charge of the electron, and this is equal to the charge of the vacuum plus E. And therefore, to find the observable charge of the whole, which represents the change in charge, we subtract off the vacuum baseline, in which case we find that the whole behaves like a particle with positive charge plus E. The key idea is this: yes, the charge of the vacuum, the total charge of all the negative energy electrons, is a huge number, and as we make our box bigger, it grows without bound. But that doesn't matter, because we define the vacuum as our reference point, the zero of charge. What matters isn't the absolute value of the charge of the whole vacuum, but the change when we remove one electron. That change is finite. The whole carries charge plus E. Even in the limit where the box becomes infinitely large and the vacuum charge becomes infinitely negative, the whole's charge stays exactly the same. That's the power of Dirac's idea. The vacuum itself may be an invisible sea of infinities, but deviations from it, like the whole, are physical, finite, and measurable. Okay, but what about the momentum of the whole? Suppose the removed electron has momentum p, and let the total momentum of the vacuum prior to removal be p vac. After removing the electron, the vacuum momentum becomes p vac minus p. The observable momentum of the whole, the change with respect to the vacuum, is then p after minus p vac, and that equals p vac minus p vac, which is simply minus p. So the whole carries momentum equal in magnitude but opposite in direction to that of the missing electron. This result is completely independent of the value of p vac. The whole's momentum is always minus p. Physically, we expect the vacuum to have zero net momentum anyway, since for every negative energy electron with momentum p, there should be another with momentum minus p, causing their contributions to cancel. Okay, so what about energy? Suppose the removed electron had negative energy E equals minus EP, where EP is equal to the square root of p squared c squared plus m squared c to the 4. And let's imagine that the total energy of the vacuum prior to removal is E vac. Then after removing the electron, the vacuum energy becomes E vac minus EP, which is equal to E vac plus EP. And so the observable energy of the whole, which is the change relative to the vacuum, will be equal to EP. And so the whole behaves like a particle with positive energy. So to summarise, removing a single negative energy electron from the Dirac sea gives rise to a real observable particle, a whole, with opposite charge and momentum, but positive energy. Interestingly, Dirac initially suggested that these wholes might correspond to protons, writing, "We are led to the assumption that the holes in the distribution of negative energy electrons are the protons." At the time, this seemed like a reasonable guess. After all, the electrons and proton were believed to be the only elementary particles in existence. But Dirac was also aware that there were serious problems with this identification. For one, his theory implied that the whole should have the same mass as the electron, whereas the proton is nearly 2,000 times heavier. Some hoped that electromagnetic interactions might somehow explain this mass difference, but the explanation felt contrived, ad hoc, and deeply unsatisfying. Further challenges came from physicists like Oppenheimer, Tamm, and Weil, who highlighted additional inconsistencies with identifying holes with protons. By May 1931, Dirac had changed his stance. A hole, if there were one, would be a new kind of particle, unknown to experimental physics, having the same mass and opposite charge of the electron. This prediction was spectacularly confirmed in 1932 when Carl Anderson submitted a paper to Science titled "The Apparent Existence of Easily Deflectable Positives." Anderson's experiments, conducted with a cloud chamber, revealed tracks left by positively charged particles that behaved like electrons with opposite charge. Anderson noted, "Some tracks seem to be produced by positive particles, but if so, the mass of these particles must be small compared to the mass of the proton, Cautiously, he concluded, it seems necessary to call upon a positively charged particle having a mass comparable to that of an electron. One of the most iconic images from these experiments appeared in Anderson's 1933 physical review paper, The Positive Electron. It shows the cloud chamber track of a particle with the same mass as an electron, but opposite charge. From its curvature relative to the magnetic field in which it was bent, and the fact that the track appears more curved above the lead barrier than below, Anderson identified it as a new, positively charged particle, what we now call the positron, the electron's antiparticle, and the first form of antimatter that was ever discovered. Antimatter was here to stay. Reflecting on Dirac's work, Anderson later admitted, "Yes, I knew about the Dirac theory, but I was not familiar in detail with Dirac's work. I was too busy operating this piece of equipment to have much time to read his papers. The discovery of the positron was wholly accidental. Despite its accidental nature, the discovery became one of the most significant validations of Dirac's theory, a bold theoretical prediction confirmed by experiment." Beyond this confirmation, the whole theory also offered a striking framework for understanding entirely new physical processes involving antimatter. For instance, if a photon supplies enough energy to lift an electron from the Dirac sea into a positive energy state, it leaves behind a hole, interpreted as a positron. The result is known as pair creation, the creation of an electron-positron pair. Conversely, if a positive energy electron encounters a hole, it can fall back into the sea, emitting radiation in the process. This process is referred to as pair annihilation. The electron and positron cancel out and only energy remains. But despite the elegance and predictive power of the whole theory, not everyone was convinced. Dirac's model faced deep conceptual resistance. Accepting the theory meant accepting a vacuum filled with an infinite sea of invisible negative energy electrons, each contributing to an infinite background of energy and charge. Even after these infinities were renormalized away, many physicists still found the idea unsettling, particularly when it came to modelling interactions in a clear and consistent way. Moreover, the framework only worked for particles obeying the Pauli exclusion principle, limiting its applicability to fermions like the electron. In the decades that followed, a much cleaner interpretation began to take shape due to Richard Feynman and Feynman-Stueckelberg, within the context of quantum field theory. The key insight was this: the negative energy solutions are interpreted as negative energy particles that travel backwards in time, and these are shown to correspond to physically real positive energy antiparticles with opposite charge that travel forwards in time. It is therefore conventional to rewrite the negative energy wave functions corresponding to U3 and U4 so that they explicitly represent positive energy antiparticles travelling forwards in time. According to the Feynman-Stueckelberg approach, the antiparticle wave functions are obtained by simply switching the signs of the energy and momentum. So, for example, if we take the wave function corresponding to U3 and replace E with minus E and P with minus P, and then simplify, we obtain the following expression. And if we then define the antiparticle spinor V2 in terms of U3, we find the following result. Likewise, if we take the wave function corresponding to U4 and switch the energy and momentum, and then define the antiparticle spinor V1, we find the following result. We'll see shortly, when we talk about quantum spin, that this labelling ensures that each antiparticle spinor mirrors the internal structure of its corresponding particle spinor. Next, we note that we can determine the explicit forms of the antiparticle spinors by performing the same energy and momentum sign switch. For example, we earlier derived the spinor form of U4, and if we then switch the signs of E and P, we find the form of the antiparticle spinor V1. And similarly, if we take the U3 spinor and make the energy and momentum switch, we find the antiparticle spinor V2. And so, to summarise, we now have a picture in which we have 4 positive energy solutions to the Dirac equation, 2 corresponding to particles and 2 corresponding to antiparticles, and all 4 now carry positive energy. Okay, so we fixed the negative energy problem, but now a deeper question arises. Why are there 2 particle solutions? And why are there 2 antiparticle solutions? Why not just one of each? What is this doubling trying to tell us? Well, it turns out there's one more hidden structure hiding inside Dirac's equation. Something even Dirac himself wasn't trying to explain. Something he didn't anticipate, but that simply fell out of the mathematics. That something was spin. At the time, spin was a bit of a mystery. It had been invented to explain certain experimental results, like the fine structure of atomic spectra, but it didn't seem to come from anything physically spinning. It behaved like angular momentum, but without a clear mechanical origin. It wasn't rotation in space, it was something deeper. In early quantum theory, spin was added in by hand to make the numbers work. But Dirac changed that, not by adding spin in, but by writing down a theory so fundamental, so rooted in symmetry and logic, that spin simply fell out. It was no longer a bolt-on, it was built in. But how do we see spin emerge from the Dirac equation? To answer that, we need to ask a deeper kind of question. Not just what are the solutions, but what stays the same as those solutions evolve over time. In physics, we call these conserved quantities, and in quantum mechanics, conserved quantities are tightly connected to symmetries, invariances in how the system behaves. So let's dig a little deeper. In quantum mechanics, physical quantities like position, momentum, and energy are represented by operators. We usually denote these with a hat, so we might write a hat to represent some generic observable. Each operator has something called the expectation value, which tells us the average value we would expect if we repeated the same measurement many times on identically prepared systems. The time evolution of these expectation values is governed by the following central equation in quantum mechanics, where H is the Hamiltonian operator, the quantum version of total energy, and the square brackets denote the commutator, which is defined in the following way. This master equation is telling us that if some operator corresponding to some observable commutes with the Hamiltonian, in other words, if the following relation holds, then its expectation value is constant in time. In other words, the quantity associated with the operator is conserved, meaning that it does not change in time. And this is the tool that we will use to hunt for spin inside the Dirac equation. To see how this all works, let's consider a simple example using the free particle time-independent Schrödinger equation, which, if you recall, takes the following simple form. We can write this as an operator equation of the form h psi equals e psi, where h is the Hamiltonian operator, which we can express in terms of the momentum operator in the following way. Now, let's see what happens when we commute the Hamiltonian with the orbital angular momentum operator, which, as you hopefully recall, takes the following vector form. If we then explicitly calculate the commutator of h and L, we see that the result is equal to 0, and we conclude that angular momentum is a conserved quantity in non-relativistic quantum mechanics. Okay, but what about in relativistic quantum mechanics? What happens in Dirac's theory of the electron? To answer that question, let's now consider the situation for the free particle Dirac Hamiltonian, which, as we've already seen, has the following form, where here it's important to note that P represents the momentum operator in 3 dimensions. If we now look at how the Hamiltonian commutes with the angular momentum operator, we find the following expression. To evaluate this, let's consider the x component, in which case we have the following relation. If we then perform the commutation on the right-hand side, we find that the only non-zero terms are those involving the commutator between py and y and pz and z, and we can then rely on the well-known position-momentum commutation relation from non-relativistic quantum mechanics to simplify, and we end up with the following compact result involving the x component of the cross product between alpha and p. We can find similar results for the y and z components, and if we then combine these results into a single expression, we can clearly see that the orbital angular momentum operator L does not commute with the Dirac Hamiltonian. In other words, orbital angular momentum is not conserved for a free relativistic particle. Now, this might seem like a problem, but it's really a clue. It tells us that orbital angular momentum isn't the full story. There's something else contributing to the total angular momentum of a Dirac particle, something internal, and that something is spin. In order to restore angular momentum conservation, we need to introduce a new operator, which we will call S, which corresponds to a new kind of intrinsic angular momentum, such that when added to L gives us a total angular momentum J that does commute with the Dirac Hamiltonian. In other words, we want S to be such that the commutator between H and J is equal to 0. Now, we have already seen that the commutator between the Hamiltonian and the orbital angular momentum operator is non-zero. And if we sub this into our total angular momentum commutator, we immediately see that the commutator between the Hamiltonian and the new spin operator must take the following form. Now, it turns out that a suitable matrix operator that satisfies this requirement is given by the following 4x4 matrix, which is defined in terms of the 2x2 Pauli matrices. A couple of lines of matrix algebra combined with the Pauli matrix commutation relations should convince you that this condition is indeed satisfied. Now, because the 4x4 operator S is defined in terms of the Pauli matrices, its components satisfy the same commutation relations as the Pauli matrices, and these in turn satisfy the same algebraic structure as the orbital angular momentum operators. More specifically, from non-relativistic quantum mechanics, we know that the components of orbital angular momentum satisfy the following commutation relations, and the components of the spin operator obey the same exact structure. That is, spin obeys the same algebra as orbital angular momentum. We also know from non-relativistic quantum mechanics that for orbital angular momentum, the total squared angular momentum operator satisfies the following relation, where lowercase l is the angular momentum quantum number associated with the orbital angular momentum operator. By analogy, we expect the squared spin operator to satisfy a similar relation, where lowercase s is the spin quantum number associated with the spin operator. If we then sub in the explicit forms for the x, y and z components of the spin operator into the expression for s squared, something extraordinary happens. All the complexity collapses into a single elegant result, 3h bar squared over 4 multiplied by psi. And by combining this with our previous equation and comparing both sides, we see that the only way that they can match is if the spin quantum number is equal to exactly 1/2. And that is truly remarkable. We have shown that the Dirac equation necessarily describes a particle with intrinsic spin equal to 1/2. Because when we say a particle has spin half, this is exactly what we mean. And now you've seen where that number comes from. Not as a postulate, not as an add-on, but as something that emerges from the Dirac framework all by itself. We didn't add spin to the theory, we didn't assume it, we discovered it. And we can now finally return to the question we asked earlier. Why are there two particle solutions and two antiparticle solutions? Why not just one of each? And the answer is spin. To understand this more clearly, let's take another look at the four positive energy solutions of the Dirac equation, the ones built from the U and V spinors, and ask what kind of spin states each one represents. Which of these describes particles with spin up, which describe spin down, and perhaps most importantly of all, what does that even mean in the context of a relativistic quantum theory? Well, as we've already seen, spin is described by a vector operator, but when we perform a measurement, we can only access one component along a chosen axis, usually taken to be the z-axis. To find the spin component of a quantum state along the z-axis, we then act on the state with the z component of the spin operator. If the state is an eigenstate of the spin operator in that direction, then the corresponding eigenvalue tells us the outcome we would obtain in a measurement of the spin component along that axis. Now, there is a subtle point. The Dirac spinors U1, U2, V1 and V2 are not always eigenstates of Sz. However, they are eigenstates when the particle is moving along the z-axis. And so, let's consider a free particle moving in the positive z direction. In this case, the momentum only has a z component, and our U and V spinors simplify. For example, if you take our original spinors U1 and U2 and set the momentum so that it's only non-zero in the z direction, then both expressions simplify. If we then take the z component of the spin operator and act with this on U1 and perform the matrix multiplication, we find the result h bar over 2 multiplied by U1. Thus we see that when the momentum is directed along the z-axis and we act with the z component of the spin operator, U1 is an eigenstate with eigenvalue plus h bar over 2. This tells us that if we were to measure the spin of a particle described by a U1 spinor along the z-axis, the result would be plus h bar over 2. And that's what we mean when we say this is a spin-up state. On the other hand, if we act with the z component of the spin operator on the U2 spinor, we find minus h bar over 2 multiplied by U2. And this corresponds to a spin-down state. It has definite spin along z, but in the opposite direction. And so we see that in this example, the two particle solutions U1 and U2 describe a spin-half particle moving in the positive z direction, with spin pointing up and down respectively relative to the z-axis. Okay, so what about the V spinors, which, if you recall, represent antiparticle states according to the Feynman-Stueckelberg interpretation? Well, here we need to be a little bit careful because, if you recall, to obtain the V spinors, we had to make the replacement E goes to minus E and P goes to minus P. And under this exchange, the orbital angular momentum of a particle changes sign. And therefore, if we want the commutator of the Hamiltonian with the total angular momentum to remain zero, then we require that the spin operator corresponding to the physical spin states of the antiparticle spinors to have the opposite sign. So let's now consider what happens when we act with the z component of this spin operator on the V spinors. If you recall, our V spinors took the following form, and if we then assume momentum only along the z direction, we find the following simplified result. If we then consider the z component of our antiparticle spin operator and act with this on the V1 spinor and perform the matrix multiplication, we find plus h bar over 2 times V1. And so we see that V1 corresponds to a spin-up antiparticle. And if we then act with the Z component of the antiparticle spin operator on the V2 spinor, we find minus h bar over 2 times V2, which tells us that V2 corresponds to a spin-down antiparticle. And so we now finally understand why the Dirac equation demands 2 particle solutions and 2 antiparticle solutions, because the equation accounts for both spin-up and spin-down states. By following the mathematics, by demanding that quantum mechanics and special relativity coexist within a single framework, we have not only uncovered the strange notion of negative energy or predicted the existence of antimatter, we've uncovered something even deeper. Particles like the electron have intrinsic spin, not because we shoehorned it into the equation, not because we added it by hand, but because the equation demanded it. Even Dirac himself hadn't anticipated this. Years later he wrote, "I was not interested in bringing the spin of the electron into the wave equation. I did not consider the question at all and did not make use of Pauli's work. The reason for this is that my dominating interest was to get a relativistic theory agreeing with my general physical interpretation and transformation theory. It was a great surprise for me when I later on discovered that the simplest possible case did involve the spin, and not just spin. The Dirac equation revealed 4 distinct solutions, particle and antiparticle, each with 2 possible orientations of intrinsic angular momentum, all of them emerging from a single, unified mathematical object, not patched on, not assumed, just there. That's why the Dirac equation remains one of the most beautiful in all of physics, a monument to symmetry, logic, and mathematical elegance from the quietest of all men. Looking back on that revolution decades later, Werner Heisenberg would reflect, "I think that this discovery of antimatter was perhaps the biggest of all the big jumps in physics in our century." And Heisenberg was right, because in solving a problem, Dirac didn't just predict a particle, he revealed something deeper, that when you demand consistency between 2 of the great pillars of physics, special relativity and quantum mechanics, the universe responds. That symmetry, logic, and mathematical beauty are not just tools for describing nature, but they are woven into its very foundations. Thank you for listening, and until next time, goodbye. And as always, a massive thank you to all my patrons, and a special shout out to Felix, Bert Humberg, Lucas Mack, and Mike Purvis. Thank you so much.